I am Chandini Jain. I am the CEO of Auquan. And I'm aware this is the last talk of the evening, so I will try to keep it not super mathematical. So we are basically a data science platform for finance. We regularly hold data science competitions with a focus on finance. We work with large asset managers and hedge funds, and we source real-world data with them, from them, and actual problems that they are working on, and we put it on our platform for a community of data scientists to solve. The community is a mix of people who have full-time jobs as machine learning engineers or data scientists, or people who are pursuing PhDs and masters in statistics, mathematics, machine learning. So super relevant backgrounds, and we make finance problems available to them to try their skill sets on, to earn monetary rewards, to get placed, and just for fame and glory. So before I get started with the talk, I wasn't sure how many people in the audience come from a finance background, so I thought I'll take some time just talking about how a trade actually happens. When you, a trader or an algorithm on your behalf, decides that you want to trade something, you basically convey that information to your broker. So what is it that you want to trade? What is the price that you want to trade it at? And what is the quantity that you want to trade, buy or sell? You communicate that to your broker, and your broker is someone who's connected to an exchange. The exchange is where all the cross of information happens. So the exchange is connected to multiple such brokers who are connected to multiple other market participants. The exchange then does a matching of the trades. So if you want to buy something and you want to sell something, instead of communicating with each other, you send all of that information to the exchange. The exchange decides that the price that you want to buy it at is the price that he wants to sell it at, and that it makes that trade happen. Communicates that information back to your broker, who then sends the trade confirmation and the actual asset that you bought or sold back to your account. So now in this infrastructure, where does machine learning play a part? Pretty much everywhere. From you deciding what is it that you want to trade, to the broker deciding how does he want to communicate that information to the exchange deciding how to make that mapping happen. But for today, we will focus on the first bit of it. So now if it's just you as a trader trying to decide what is it that you want to trade, what goes into that, if you want to do it in a fully automated, data-driven, machine learning-driven manner. How to identifying a trading strategy. So what is it that you want to trade? Which markets do you want to trade? What is your trading logic? How do you want to trade that market? And what are the parameters that will trigger that trading logic? Once you've identified a trading logic, you backtest your strategy. So how does your strategy do on historical data? And by doing that backtest, are there any biases or inefficiencies in your strategy that you can remove and make it more profitable? Then actually executing your strategy, so connecting it to a brokerage and trying to minimize the transaction cost, the cost that you pay to your broker to make that trade, the cost that you pay to the exchange to make that trade, and any slippage that you might incur because you don't get to trade at the price you wanted to originally trade at. And finally, managing your risks. So putting checks pre and post trade in place to make sure you actually send the order that you want to trade, and once you get a confirmation, did you actually trade what you originally intended to trade? The idea here is that developing a profitable trading system is way more than just finding an amazing idea. It is finding a great idea, validating it, backtesting it for your system, and then making sure you have good execution and good risk management in place. So for today, because I only have limited time, we're going to only focus on the first bit of it, which is identifying a trading strategy. And when I like to think about identifying a trading strategy, this is what I like to call my trading strategy flowchart, how I think about going from raw data to actually deciding what is it that we want to trade. So you have a bunch of real-time data that is coming into you from an exchange, and you also have a bunch of historical data in the past about what happened with the price, the volume, what happened in the markets. All of that data goes into something which I'm calling here the prediction model. The prediction model is something that just makes a forecast about the future. The forecast can be anything. What is the price of Apple stock going to be tomorrow, or is the stock going to move up or down? It is just something that is not known today, and you make a forecast about it in the future. Once you have a prediction, the prediction goes into something that I'm calling the trading signal. The difference between a prediction and a trading signal is, once you have a prediction, what do you choose to do with that prediction? If I know that the price of a stock is going up tomorrow, do I want to buy it tomorrow? If I know that it's going to go up 3 consecutive days in a row, or if my prediction model says it's going to go up 3 consecutive days in a row, which day do I decide to buy it? So the trading signal takes your prediction and converts it into an actual actionable trade that you want to take. So do you want to buy or sell, and at what price do you want to buy or sell? Then you combine that with, in a trading strategy, with the capital that you have available, any risk limits that you might have in place. I'm not allowed to buy more than 100 stocks, or at any given point in time I cannot have more than 10 stocks of any given asset in my portfolio. Combining all of those constraints and all of those limits that you have in finally deciding what is the order that you want to send to your broker. The final order that you send to your broker, the end goal of any trading strategy is a final trading action. Buy or sell a certain quantity of a certain tradable asset. So buy X shares of a certain stock at a price below Z, for example. To be able to identify, to be able to send that action, you need to be able to identify what is the direction that you want to trade. So is this asset expensive or cheap? Do you want to enter or exit a trade? If it is cheap, do you want to buy it right now? If it is cheap and you hold a short position, do you want to buy your position back? So do you want to enter or exit a trade? What is the range you want to trade it at? So at 100 it is cheap. When you send that order, it might be trading at 101 or 102. Do you still want to buy it at that price? And how much of it do you want to buy? Deciding all of that goes into the final trading action that you will send to your broker. So how do you actually make that trading action? And how do you make it using data science? Step 1, deciding what is it that you want to trade. Which region do you want to trade? Do you want to trade Europe? Do you want to trade the US? Do you want to trade Asia? Do you want to trade Japan and Korea? Which security do you want to trade? Do you want to trade fixed income or equities or foreign exchange? And a bunch of things go into deciding that. How much volume is available in the market? What is the fee to actually trade that? What are the capital requirements to make those trades? Let's assume you've sorted all of that out. How do these securities actually behave? Do they display mean reversion behavior? Do they actually just go up and down around the mean price? Do they exhibit momentum behavior? So if price has gone up today, price is very likely to go up tomorrow. And what is the availability of historical data for you to actually develop your model? If something started trading 1 or 2 years back, it is unlikely you will be able to trade it in an automated manner. And then how do you want to trade it? So creating features from this historical data that is now available to you that help you identify a trading logic that you are going to use. And the features can be anything. It can be starting from simple price to some technical indicators. How do these securities actually behave? Mean reversion, momentum, do you want to do a pairs trade? Do you want to buy something and sell something against it? And finally, generating a trading signal using these features and how these securities actually behave to decide if this instrument is a buy, sell, or do nothing. Now, before I go into the machine learning part of it, there are 2 approaches in finance usually to building a strategy. One's a data mining approach and a model-based approach. In a data mining approach, you just look for patterns in data. It doesn't matter what is causing that pattern, as long as you can with some level of confidence say if a pattern has happened in the past, it will happen again in the future. And that's all you need to know. You don't need to know the fundamental drivers behind what is making that pattern happen. The problem with this approach is it's a blind approach. You're literally just throwing some darts at the board and trying to figure out if something will happen in the future again, and you need to be able to identify what is real from a random pattern that you might have got. So that this approach is very, very prone to overfitting. But if done well, and this is the approach that machine learning tends itself to, done well, you can get some really profitable trades out of it. The other approach, the model-based approach, is you start with a fundamental view of the universe. You say, these are the factors that drive my prices, and now I'm starting with a simplistic view of the world, already knowing what is driving prices. I'm going to try and build a model that explains it. You construct a mathematical model based on your understanding, but it's very likely it's a very simplistic model that omits a lot of variables that actually affect prices, and you need to be very careful knowing what are assumptions and what are real factors that are driving those prices. So good and bad about both the models. Obviously, machine learning lends itself really well to the first approach, which is the data mining approach. For the next 10-15 minutes, I'm going to talk about how we apply machine learning to actually making predictions of what to buy and what to sell in finance. I'm assuming that you already have a background in machine learning, and I'm mostly going to talk about what is it that makes it very specific to finance. But just a quick recap before that. So a standard machine learning workflow looks like this for time series. You have a bunch of data. The data is time-stamped. You have some features which is available to you. So this is historical data about things that have already happened in the past. And you have a target variable y that you are trying to predict. For historical data, you also have the value of that target variable. So using these features, you're trying to predict the value of y and hoping that you get a model that as you go forward in time, when these new features become available, but you don't have the value of the target variable, you are able to actually predict the value of the target variable. So using historical data and historical value for target variable to develop a model that will then, as you go forward in time and new feature values become available, allows you to predict the value of the target variable. So now if we're trying to do this for, let's say we're trying to set up a system that is actually that you want to use to make forward-looking predictions about something you want to trade. What is the first step? It's obvious, setting up your problem. What is it that you're trying to predict? Are you trying to predict prices? Are you trying to predict profits? Are you trying to predict if an asset is simply a buy or sell? Will the price go up or down? Are you trying to optimize your portfolio? So are you trying to decide what is the optimal allocation to different assets in your portfolio? Are you trying to predict efficient execution, or are you trying to do something even more complex like reinforcement learning? So if I go back to our sample framework, that target variable, what is y? And y can be price at a future point in time, just the direction of price. Is the price going to go up or down? Or what the returns are going to be at a future point in time. But it sounds super simple, but before you actually proceed forward, and the step, what you decide here, what y is going to define how the rest of your trading system builds out. If you try to predict prices are really hard to predict, very high error, but the execution that you've decided on prices will then revolve around what your confidence interval around the price you're predicting is. Versus if you just try to predict the direction of price, easier to predict, but you have to be aware, just predicting price will go up or down conveys no information about how much price will go up or down. Sometimes you might end up making trades which should be profitable because price did go up, but it didn't go up by as much as you had to pay to make that trade. So deciding, the step you decide here, what is it that you're going to predict, will define how you build the rest of your strategy. So it's just being super aware of what is it that you're trading and what makes the most sense for the system that you're building here. The second step, once you've decided what is it that you're predicting, how will you evaluate that you actually have a good model? And that will depend on what you've chosen to predict. If you've chosen to predict prices at the next instant in time, you probably want to use something like a root mean square error to decide what is it that you want to evaluate. But if you've decided to, for example, predict something like if you have a mean reversion model and you want to predict if it will go up above the mean or below the mean, you will probably have a high root mean square error because the value tends to fluctuate around the mean quite a bit. So root mean square error is probably not the right metric for you. So what you choose to predict and how that behaves will define the metric you use to evaluate your model. And it's super important to get this step right, because if you choose the wrong metric to evaluate your model, you might end up using a model which is actually not the most accurate or the best fit for the system that you're trying to use, but you just have chosen the wrong metric, and that tells you this is the right model to use. So I want to do this by an example. One of the problems that we were trying to solve on our platform was trying to build a prediction model that could help you predict the price difference between two assets. So what is the difference in price between asset 1 and asset 2? The target variable that we chose in this case, after a bunch of research, was we want to predict the future expected value of that difference in price. So I want to predict over the next 10 minutes, what is the average of that value going to be. My objective was to create a model so that that predicted value is as close to the actual average value over the next 10 minutes. So I chose the root mean square error as my evaluation criteria. This is just a sample of the data. So I have price of asset 1, I have price of asset 2. The column called basis is the actual difference in prices between those two. And my target variable at every point in time is the average of that value in column 3 over the next 10 minutes. That is obviously not information that's available to me at that point in time. I just want to be able to predict it because then I can use that forward in my trading strategy. Step 2. So you've decided what is it that you want to predict to go into your trading system. You've decided what you want to, how you want to evaluate that. The next step, the obvious step, is collecting reliable data. So collecting and cleaning data that actually helps you make that prediction. And this is where your domain knowledge comes in. What sort of data will actually have predictive power over my target variable? In this case, if I'm looking at the problem that I'm trying to solve here, probably the price of the stock, the trading volume of the stock, some sort of fundamental market data, something about that overall market, maybe something about the correlated assets, other assets that are correlated with this price that I'm trying to predict, other correlated stocks and correlated assets. So for example, if this is an airline stock, then oil prices might be predictive. The next step is then obviously checking for accuracy of the data. Is the data clean? Is there any missing data? If you're working with data around equities or fixed income, also cleaning data for things like dividends. Dividends are super important because if a dividend comes out, the stock price drops, you might think the stock price has dropped, but it's not actually a change in price. It's just that they have paid out a bunch of their market value as dividend, which is why the stock price looks lower. Probably you want to work with alternative data. This is just a bunch of examples of the kind of data that is not standard, non-standard financial data that might have information about the system that you're trying to predict. Step 3. And this, I think, is the most important step that determines if your strategy is going to be successful or not, is creating training, cross-validation, and test data sets from the data that you have at hand. So we started with a sample framework which looked like that. You've got a bunch of historical data and you want to make future-looking predictions using that data. And probably everyone here who is doing any kind of machine learning is aware of the training, validation, test data split. You start with training, so you take your entire historical data that's available to you, you break it down into training and test, and you say, of the training data, I'm going to train my model on this data. I am going to test how well that model does just on the validation data. If my model does not do well on the validation data, I'm going to go back and change some parameters and retrain my data. I retrain my model using my training data. I'm going to test it again on validation data. I'm going to keep doing that over and over and over until I get to a point where my error or whatever the metric that I'm evaluating it is up to a desired standard. But by doing that, what you've done is this validation data that you've not trained your model on has actually slowly become a part of your training data, because you're using the information from this validation data to decide if your model is good enough or not. You train a model on 60% of the data, you test it on validation data. If your metric is low, you go back and retrain it. So you have this information that the model that I've built at the moment is actually not good on validation data. And if you do repeated iterations of this, at some point, your validation data becomes a part of your training data. Which is why it is important to have that third layer of data called the test data. This is out-of-sample data that I'm not going to touch until I have a final model that I'm happy with. I'm happy with the performance of that in validation data, and I'm going to go and test it on my test data. The test data is something that until that point in time, I have absolutely decided not to touch. So you train your model on the training data, you keep some part of your data as validation data, you go that loop of training, validation until you build a model that you're finally happy with, and you test it on test data. If your model at this point does not do well on test data, you just discard it and you start afresh. You do not go back and retrain your model. If you retrain your model, you're contaminating your test data. And this is extremely important, especially in finance when it's super easy to overfit. It is absolutely important that you keep your test data uncontaminated. But one of the problems with this approach, and the biggest problem with this approach in finance, which doesn't happen that often, regime shifts. So if you're trying to build predictive models for the world, people don't change, physics doesn't change, but markets unfortunately change quite a bit. So you might have built something, you might train it on data from 2017, from January 2017 to March 2017, and you test it on from March 2017 onwards. So you've trained it on a regime which was behaving very differently from the regime that you've tested on. You might have built a really good model that performs really well in the first bit but will not perform well, and it hasn't even seen that spiky bit right there to actually learn from. and this is one of the most challenging bits when you try to build models for finance. You might end up training on past information that is actually not even relevant anymore. And you might end up training on a regime or a situation or market conditions that don't even exist anymore. So one of the ways to fix that is doing a rolling cross-validation. So let's say you have 20 years of data, you train on 5 years of data. You validate it on the next 1 year of data. If your model doesn't do well, you change some parameters and you train it on the next 5 years of data. And then you retrain, you check for your metric on next 1 year of data, and you keep doing that. So you're training on 5 years, testing on 1 year, then training on the next 5 years, testing on 1 year, and you keep doing that until you get to a model that you're happy with. But the caveat here is you've trained your model on different regimes and you've tested on different regimes as well. And hopefully by doing that, you come up with a model that will perform better on multiple regimes instead of just performing on the regime that it's been trained on. And then you have your final test data where you test your model. Ideally, your test data also comprises of some bits of different regimes in the market, but then you run into problems of continuity. How do you deal with the fact that you've got bits and bits and bits from different time series? But at least doing a rolling training validation solves for the fact that you might end up training on situations or market patterns that don't exist anymore. All right, so we've decided what we're going to predict, and we have created a training validation test split, and we have promised ourselves we're not going to touch the test data until we have a model that we're actually happy with. Finally, creating features. And the golden rule of feature selection, especially in finance, is the predictive power of the model should come from the features. The predictive power of the system that you're building should come from the features and not from the model. What that means is if you've chosen your features really well, it almost doesn't matter which model you use to make your predictions, because you've chosen features that actually have signal about something that you're going to predict. And if you've chosen bad features, especially in a data set which is mostly noise, has a very weak signal, you might end up, and if you see a lot of variation between predictive powers of different models, you might end up with an overfit system because your original features did not have any information about what you're trying to predict itself. So it's one of the tests that we do is trying to train our model using different classifiers or different models to see, is our feature quality really good. This is the most important step. If you are able to identify good features which have good predictive power, you've done 90% of the job. The point I'm trying to make here is the choice of feature has a far greater impact, a much, much greater impact on what you try to build than the choice of your model itself. Some of the do's and don'ts here, which apply in general to any machine learning workflow: don't randomly choose a very large set of features. Don't try to just think all the information that is available about the system, I'm just going to use all of that to predict my target variable, because it is highly likely you will end up introducing random noise into the system, which is unnecessary, or you will end up randomly overfitting to a pattern, which means nothing. Little or no relationship will lead to overfitting. One of the things that we try to do is rank candidate features according to correlation, according to information criteria, according to PCA, just trying to identify features in advance which have some information. Also trying to group multiple features which have the same information about the target variable into one feature. And that's important because, again, if you have a bunch of features which have the same information but a random component, you're unnecessarily introducing noise into your system. Now, here's where things get interesting. If you look at any other system about machine learning, it is almost always advised that you normalize or transform your features and you try and get them into the same scale. In finance, that becomes tricky because the future range of data is unknown. And also, if you're trying to normalize, if I have, let's say, data over 20 years and I take the average of value over those 20 years and I try something like a scaling, I am using information from the future to normalize my data from the past. So if I take an average of the data over all 20 years and I say I'm just going to divide every value by the mean, then at the start of the first year, I have used information from the future which wouldn't be available to me at that point in time to normalize my data. As you keep going forward in time, you wouldn't know what the average is going to be over the next 20 years, if that is the normalization that you choose to use. So, and it's also possible, let's say if you've tried to normalize your data to a -1 to 1 scale, it is highly likely that eventually in the future, your data might go out of that range and you will end up with features that are +1 or below -1, and that's just because because markets keep changing and because the future range of data is not known. In any of these methods, the other thing to be aware, one of the ways that we fix it is we try and use a rolling mean. So I take 5 years mean and I normalize everything in year 6 by the trailing mean of the 5 years, and I take the mean of 6 years and I normalize everything in 7th year by the mean of the last 6 years. The thing to note here is if you're trying to do that, so if you're trying to use a rolling mean or an expanding mean to normalize your data, then even if the feature value remains the same, the transformed value might change just because the mean has changed. So the mean over 5 years, if the mean over last 5 years is 5 and your value is 20, then your data normalizes to 4. If the mean over 6 years then is 4 and your data is 20, your value normalizes to 5. So the same feature value might lead to a different normalized value because you're using an expanding or rolling mean. But if you don't use an expanding or rolling mean, then you're probably overfitting or introducing some look-ahead bias into your system. So it's sort of a delicate balance in trying to see which one works for your system. Sometimes normalization works, sometimes it doesn't work. I don't have a handy, this is what you should do. It's just a trial and error method and being aware of what the pitfalls of each of them are. Alright, so finally, model selection. So choosing an appropriate machine learning model based on your problem that actually solves your problem, and then training, validating, and optimizing the system. So coming back to the problem that we were talking about at this point, I'm trying to predict the difference between the prices of two assets. I have decided my target variable is the actual the expected value of that difference in price over the next 10 minutes. I have used data that I think is actually predictive. I have cleaned this data and I've created some features which I think should be relevant. And I start with a super naive approach. So I take lots of random features. I create every possible feature that is known to me, every technical indicator that's known to me, and I fit a linear regression model. This is the first result that I get. My root mean square error at this point is 0.25. And the standard deviation of my target variable is 0.59. So it's not amazing. It's okay. It's not that bad. I get a P&L of 8% using this strategy for 3 months, 6 months. What can I do here? I'm using a ton of features and I actually don't know which features are important or not. So I try and normalize my features. In this case, I'm doing a rolling normalization. So I'm saying I'm going to look at the historical 30-minute mean and historical 30-minute standard deviation, and I'm going to do a normalization of my features. When I do the normalization, my performance doesn't actually improve. My performance drops and my P&L drops. But what normalization does, pre-normalization, some data was in the range of 0.5 to 0.25, 1.25, some data was in the range of 5,000 to 10,000. So when I'm looking at these coefficients of my linear regression before normalization, they actually don't mean anything. I don't know if a feature with a coefficient of 19.11 is more important than a feature with a coefficient of 0.05. But after normalization, I can look at the coefficients and decide which features are important and which features are probably not important, because now my data has some sort of a scale to it which is similar across different features. So I look at some features and I know which features are important, and I discard the features which I think are unimportant, and I run my regression again. And when I'm running the same regression, I'm seeing that I run the regression again, but on unnormalized data, but removing features which I thought were irrelevant after normalization. My performance does not drop. I get the same P&L, and I've removed a ton of features which are actually just noisy and irrelevant to me. So even though I'm not using a normalized feature model anymore, normalization just helped me figure out which features were important, which ones to drop, and hopefully removing some noise from the system. If you compare the P&L, pretty similar P&L profiles. Before and after removing features which were irrelevant. And then we tried doing a bunch of other more sophisticated learning algorithms, not linear regression. So we tried an SVR. My root mean square error drops, my P&L improves. I try a gradient boosting regression. My root mean square error is even lower, my P&L is amazing. I found an amazing model which I think does really, really well, and this is what I'm going to use to make my trades. But the next step. Backtesting on test data. So remember that data that at the start of the model that we had said we're not going to touch until we have a system that we're happy with and has low error, and now we want to test it on real out of sample data. This is data that my system is not aware of, and it is almost representative of if I decided to put this system into production, the new future data that would be available to my system, how would my system do on that? So this is how my regression model does on my outer sample data. Okay, it's root mean square error, okay P&L, but I'm super excited about my gradient boosting model, and surprisingly it does exactly the same, just marginally better than my regression model. And this is the biggest problem with finance. You can build models that do really, really well on training data, but when you actually put them into production, when you put them on data that it has never seen before, you don't get the same amount of performance. You can speak to so many people that will say, I built a model, did really well in backtesting, did really well in training data, but just failed in production. The biggest problem is finance is so prone to overfitting. There is so much noise in the data, there is such weak little signal in the data that if you don't go about the specifics of this entire workflow well, you will end up with models like that gradient boosting model, which does really well on training data, doesn't give you any extra performance. What probably ended up happening is some of the features that I was using there, my model ended up learning a market regime shift, or it ended up learning, one of these patterns there really well, and it was doing really well on training data, but when I actually started to test it, that situation that was very specific, that my model learned, does not happen again in the future, and that information that it's learned and that's giving it that extra boost in performance is actually relevant. So one of the things that we've learned after building multiple models to multiple competitions is the simpler your model is, the more explainable your model is. If you can look back at your model and understand exactly why is it making the predictions it's making, what is the data that's feeding into it, how is it using those features, which features are important, do those features tie in with my intuitive understanding of the system, it's less likely the model is overfit. Even if it does well on training data, you will avoid overfitting on test data. One of the ways that we deal with something like this is if we find multiple models that do well, we try and use something called ensemble learning. So I might train something, a KNN, a linear regression model, an SVM model. I take predictions of all of those models. I combine them together and I use that as my predicted target variable. The hope here is that each of those models have different errors and have some predictive element to it. So if I combine them together, the errors hopefully average and cancel out, because each of those models has a different component of error, but the actual predictive value holds, and my actual predicted final target variable does better than any of the individual models itself. I guess I'm pretty much running out of time. So just some do's and don'ts before we close this. Avoid overfitting, super important in finance. It is so easy to build models that are overfit, that will look promising, not do well in real life. Do not retrain after every data point. This is something that we see regularly. If you're building a model that is making predictions, let's say on a 10-minute basis, and you've given it 5 years of historical data, and if you need to, in 10 minutes, markets don't change dramatically. But if you need to retrain your model after every 10 minutes, you've probably ended up with something that is not stable, that is not predictive. If you find the performance of your model deteriorates, if you haven't trained it after 5% of the data that you have historically, you've probably ended up with something that is overfit. Avoid biases, especially look ahead bias, and this is another one that happens to a lot of people very often. Somehow in the information that you're using to build your model, you've ended up using information from the future without realizing it, maybe in the way you've created your features or in the way you've created your target variable. So testing your model, making sure there is, at any given point in time when you are testing the performance of your model, there is no information from the future that you're using to make those predictions, because when you actually go to put that model in production, that information won't be available to you. And be wary of data mining bias, what we talked about right at the start. The way we are building these models is we're saying we just want to find patterns that repeat themselves over and over again. We don't care why those patterns happen, as long as we can say with the certainty that these patterns will happen in the future. So being aware, it is highly likely that if you follow this approach, you might end up catching a random trend which is not actually predictive of anything, and testing for that. The last bit, I like to say this over and over because it's one of my biggest pet peeves. This is one of the things that makes trading strategies fail: overfitting. You have not learned anything predictive about the model. You just learned something in the past that happened that might not happen in the future. So a complex algorithm will perform wonderfully on training data, but when you put it into production, will just fail miserably because you've overfitted. So the simpler your models are, the more explainable they are, the more intuitively you can understand what is that your model is doing, the more likely it is to succeed. All right, thank you. The second part, which I didn't go into, was actually how you put that strategy into production. So in this case, we analyzed the system and felt that 10 minutes was the way we wanted to use this model. Was then, now that we know the average price, if the price goes higher than average, I want to sell it. If it goes below the average, I want to buy it. And we found it was mean reverting over 10 to 15 minutes. So that's why we chose 10 minutes as the ideal time. Yeah, over 10 minutes. Yeah.
Any guarantees for the ensemble learning that it will actually perform better than single model?
There's no guarantees, obviously. If you have one model that is highly predictive, that is likely to perform better than an ensemble model. The idea behind ensemble learning is you have a predictive component and you have noise, but hopefully different models have different noises. So when you combine them together, the noise part gets averaged out and the predictive part gets so if you have something like prediction plus noise 1, prediction plus noise 2, prediction plus noise 2, when you take the average, the prediction part holds stronger. But if you actually have a very predictive model, then ensemble will not do well. Overall, probabilistically, it is more likely that ensemble does better.
Are you aware of bagging, where it's a bit like ensemble, but you actually play around with how you divide your tests and validation? Have you tested it and does it work well?
In some cases. So again, I cannot say conclusively that bagging works better, ensembling works better. And there's again this element of we've tested it on test data and then we're saying this works better. If I test both on my test data, I've sort of contaminated my test data. What I would like to do in that situation is try both, put both into production, see which one does better over newer data that I haven't compared either over, and then decide.
Just one last question. So you said that feature engineering is the most important part. So have you ever made a judgment call saying that I think these features are important, but the error is still bad with these features, but still I will use it because it's a judgment call?
We have. I've worked with clients who've said this feature, even it's the other way around. If I remove this feature, the performance of my model drops, but it just intuitively does not make sense to me that this feature should be predictive of what I'm trying to predict, so I'm going to remove it because it's probably just overfitting to, again, a random trend.
In the first slide that you show, you have this automatic pipeline of, the broker, the stock exchange. Do you have the time for making such judgment calls?
It's before you put the model into production, not at the time. When you're building this model, you say, I built a model, it's looking at these 10 features, these 8 make sense, the other 2, I really have no idea why, I don't know, the number of footfalls somewhere should be predictive of bond prices somewhere else, so I'm just going to remove that because it just does not make sense.